Warm greetings. The South African Mathematics Foundation, whose website is www.samf.ac.za, conducts several competitions aimed at high school students during the course of each year. Amongst them are the Olympiads, the juniors and the seniors, and these Olympiads run over 3 rounds. In addition to the Olympiads, the foundation also administers a competition called the South African Team Competition, in which several teams of 10 participate. Over 50 teams participate in each division, namely the junior and the senior, and these learners are given 2 examinations or two tests. One is called the individual and the other is called the team competition. The team competition consists of 10 problems, rather challenging problems, and the entire team tries to solve those problems. So today we are going to do, this series is directed towards unpacking the solutions of all these competitions that I mentioned from 2023 to 2025. So today we are going to do the senior team competition, which was set in 2025. So with those few words, we will go straight to the as you can see, it is the 2025 senior team competition. Okay, the very first question is, let n be a 3-digit number such that n is equal to m squared. So the n is a number which is a square number. It's a square of another number. Now, there are just a few relatively 3-digit numbers which are squares. Determine all the numbers n having the property that the sum of the digits of n is equal to the square of the sum of the digits of m. All right, so let's try to solve this problem. So what do we have? We have that n is equal to m squared. And n is a 3-digit number, so we can say n is 100th digit, 10th digit, 100th digit. But I normally put this like this to distinguish it from a product of A, B, and C. And this is equal to the square of m. Now, which numbers have the property that the squares are 3-digit numbers? All right, so m, the lowest value m can have is 10. 10 squared is 100, and that's the lowest 3-digit number. So m can be 10. The highest 3-digit square is 31 squared. And because 31 squared is 961, well, 32 squared has got 4 digits. So n can be any one of these numbers from 10 all the way up to 31. Now, it's also given that the sum of the digits of n, let's call it S, sum of the digits of n, and the sum of the digits of n are a plus b plus c. And that is equal to the square of the sum of the digits of m. So this is S of m, the sum of the digits m, square of that. Now, the highest possible value that a plus b plus c can have is 27, because a is the digit, you see, and the digits run from 0 to 9. So that means that S of m is less than or equal to 5. So the sum of the digits of m, this two-digit number, is less than or equal to 5. So let's write down all these numbers. You can start from 10. 1 plus 0 is less than 5. 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, it stops there. Right. Now you can start with 2. 2 plus 1, 2 plus 2, 2 plus 3, it stops there. And 3, you can have 3 plus 0, 3 plus 1. And 3, oh, you're not allowed to go to 3 plus 2 because it only goes to 31. So we've restricted the numbers to just these few. These are the possible values for m. Let's put this into a box like this. This is your m, and your n is m squared. So let's just separate these things. Sorry, this is not very neat. Okay, that's m, and n is m squared. So this is 100, 11 squared, these are the squares of these numbers. 22 squared is 484, 529, and 900, and 961. Now, it's given that Sn is equal to Sm squared. So what is S of m? Some of the digits for m are 1, 2, 3, 4, 5, 3, 4, 5, 3, 4. I'm looking at the sum of the digits of m, and I want to look at the sum of the digits of n. The next one, that 1 plus 0 is 1, 2 plus 1 plus 1 is 4. 144 is 9. 169 is 16. 196 is also 16. 441 is 9. And what is 484? That's 16. 529 is 16. 900 is 9. 16. And we want to know whether you got S of n is equal to S of m squared. So when you square this, yes, 1 squared is 1, 2 squared is 4, 3 squared is not 4. Why did I say it's 4? 4 plus 4 plus 1 is 9. So 144 is, the sum of the digits is 9, not 4. Let me just correct that, sorry. So 3 squared is 9, 4 squared is 16, this is out. 3 squared is 9, 4 squared is 16, this is out. 3 squared is 9, 4 squared is 16. So now you know what the numbers are. They say determine all the numbers n having this property. And so you can see n is the first 4, 100, 121, 144, 169. It is not 16. It is not 5. Right? And it's not this one here. But it's all the others. These are the only ones which don't work. Okay, so there are 8 different numbers n which have this property. Okay, so that takes care of the very first problem. I always write down the solutions in advance. So let's just see whether my prepared solution. Okay, I think there are 8 of them there. So that should do the trick. So it's almost the same solution as the one that I did. Okay, now question 2. Regular pentagon ABCDE is centered at the point O. All right, so the center, by center you mean, you see every regular figure, whether it's a regular polygon, which is the one that we see here, or a regular hexagon or a regular septagon, all these regular polygons, they have the property that their vertices lie on a circle. In other words, the vertices of any regular polygon are concyclic. You call it concyclic. So that doesn't happen generally, but in regular polygons it happens. So that is why they can speak about a center. It means the center of the circle that contains the 5 vertices. So O is the center. And you got these perpendicular, which are dropped from this vertex. And these points are all named. And the problem is to calculate AO plus AY plus AZ. In other words, the sum of the 3 lines, there are 5 of them. Anyway, you just want the sum of the 3 dotted lines from AO, AY, AZ, and you want to add all of them. All right, so we need to calculate these. You can try, as I did, to try to calculate. We let the sides be, give a name to the sides of this regular polygon. Let's call them. All the sides are equal, by the way. And then we can give a name to the radius of the circle, R. And I try to get equations involving A and R to solve, and then to work out the sum. And I have to say that I used a lot of trigonometry and so on. I couldn't come to it. It became very complicated. So we have to use another strategy rather than find these. A careful examination of this says the following. We can regard these AZ as the heights of triangles. The triangle that we will have these heights are this one here, the one with base ED, it's perpendicular to ED, and with vertex A. This triangle has got that as a height. Likewise, this is the height of this triangle here. So when you split this polygon into three triangles like this, then it turns out that these are now the heights, and these are equal. This is also A here. So that it gives a suggestion that we calculate the area of this polygon ABCDE. So let's try to work out the area of ABCDE. So it's this triangle AED. I mean the area. By abuse of notation, I'll use this to depict the area. And the next to the middle one is ADC. And the one on the right is ACB. And the nice thing about these, that's why the strategy is interesting, because these become the heights. So they will feature here. The area of triangle AED is half base. There's your base is this times the height. The middle triangle is half base, which is AY. Base is A. The base is A, but times the height, which is AX. Now, why is the height of this AX? How do we know that this is 90 degrees? Well, you can see by symmetry. This is right at the center. So this line here that goes through the center, it splits this polygon into two equal parts. So therefore, this will have to be 90 degrees. Okay, otherwise you can actually calculate these angles, and you will see that yeah, okay. I'm not going to go into that. This is 90 degrees because it splits this thing up into two equal parts. All right, so this is AX is the height, and the other triangle is half A. This time, this is the base times AY. Now, that's one of the ways of calculating the area of the triangle, the area of this polygon. But there is also another way, and that is by joining the center to the 5 vertices. If you join the center to the 5 vertices, because this is the center, all these will be equal. These triangles, I'll shade one of them. Let's shade this one here. All these triangles are actually congruent. You see, because as I said, these points lie in a circle, so this becomes a chord of the circle, and this chord here subtends this angle EOD at the center. So equal chords subtend equal angles at the center. So it means that all these triangles are all congruent. And the radii, actually, because for 3 sides, all these are radii. So these triangles are congruent, so they all have the same area. So this is equal to 5 times the area of any one of these triangles. And I've just shaded this area of this triangle. Let's take the area of this triangle. This is a half base, that's DC, times the height, OX. But it's given that OX is equal to 1. I should have mentioned this. OX is actually equal to 1. So you have that situation. All right. Now, so you got the area of this polygon in 2 different ways. All right. One is equal to 5 times the area of each of these congruent triangles. And the other is what we've done here. If you look at this, you'll see that A is cancelled right throughout. A is, and even the halves. So if I take out the half A, half A, half A, half A, I have AZ plus AX plus AY is equal to 5. So we're almost there now. You got AY and AZ are here. The only thing is you got an AX. But AX is AO plus OX. This AX is AO plus OX is given that OX is 1. So it works out very nicely because now you got the 3 things that we wanted, AO, AY, AZ. And all you have to do is to take this 1 to the other side. And you got your answer. The answer is 4. Hi, this is, you have to have the insight to notice that you can get an equation because the area of this polygon can be calculated two different ways using the heights that are given. Once you have that realization, then the rest of it falls into place. Okay, so that takes care of, so we said the answer is 4. Let's just check to see. Yeah, so we did this thing in exactly the same way. All right, and the answer is 4. Okay, so let's get on to the next problem. Now here you have, find a value of theta. So theta is an obtuse angle, so that you got this funny looking equation here. You got 5 plus 2 root 6 to the power of sine theta. Oh, that's a nasty piece of work. And this is 5 minus 2 root 6. Okay, these two are nicely related, to the power of sine theta is equal to 2 root 3. Now root 3 is related to sine in some way, because we know the sine of 60 degrees is root 3 over 2. All right, so how do we work this thing out? It's an exponential equation. The theta, your unknown, is sitting at the top there. Now, it turns out that these numbers here are actually square numbers. I think you have that 5 is 1 plus 4. So I think you'll have to have a root 3 or something. So maybe you've got, let me try 2 plus root 3 all squared. Okay, that'll give you 2 plus 3 is 5. So, okay, I need a 2 root 2. Okay, see, square root of 2 plus square root of 3 all squared is 2 plus 2 root 2 times root 3 is root 6. That should help. This is root 2 times root 3. And plus 3, and that is equal to 5 roots. 5 plus 2 root 6. So this quantity here is a square, right? And I think we can see quite quickly that the other one will be root 2 minus root 3 all squared. And that gives you 5 minus 2 root 6. All right, so these numbers here can be written as square root of 2 plus square root of 3 all squared, and that is to the power of sine theta. So you can make 2 sine theta plus, here you have root 3, root 2 minus root 3 to the power of 2 sine theta is equal to 2 root 3. Now you see that this 2 root 3 is really the difference between these two. It's really the difference between these two. You have to subtract them. And so it looks as if this thing here should be equal to 1. Wait a minute. Instead of root 2 minus root 3, I can write, you see, when I take the difference between these two, I want to say that this is 1. So, but then when I add this, then I have to add this, you see. And that doesn't give you 2 root 3. But if I turn this thing around, instead of root 2 minus root 3, I can put root 3 minus root 2. Whether you square root 3 minus root 2 or root 2 minus root 3, you'll get the same thing. A number and its difference, it's negative, the square comes to the same result. So why do I say this? Because, and then the left-hand side equals root 2 plus root 3 plus root 3 minus root 2. Because if this is equal to 1, and that is 2 root 3. So finally, you got this equation 2 sine theta is equal to 1. So sine of theta is equal to half. And theta is equal to 30 degrees. Sine of 30 is half. But you want the angle to be in the second quadrant. So sine of an angle in the second quadrant is also equal to a half. So it's 180 minus 30 is the other solution. We need to take this out, and the answer is 150 degrees. Okay, so this can be worked out if you know that this is a perfect square here. But you can see this is, the 6 is 2 times 3. So the middle term, this second term is 2 root 3. So it looks like 2ab, you see. So you can write this thing as a squared plus 2ab plus b squared. All right. So the answer is 150 degrees. Okay, it's exactly the same solution. All right, so that's fine. Okay, we go on to question 4 now. It says the real numbers A1, A2, A3, and so on. Oh, no, A0. Start from A0. The writing is quite small. Sorry. Let me write this thing clearly. I can read it from where I am sitting. So this equation here is A m plus n plus A m minus n equals A 2m plus A 2n all over 2 where this m is greater or equal to n. You need to have that because this has to be starting from 0, you see. Right? The lowest value for the subscript is 0. So m minus n must be greater or equal to 0. Okay. Now, they ask us to calculate A 2025. Now, these kinds of problems can be quite difficult or tricky, but you have to try to, get various equations because you see, you've got infinitely many equations here. M and n are any integers. They should say m and n are integers. Because the subscripts are all integers, you see. So because you got a lot of possibilities for m and n, you can try out substituting various things, get equations. And many equations you can substitute. Like for instance, now, if you let m and n both be positive, well, equal to 0. Right? See, n can be 0, but m is greater than. So if m is 0, then n is also 0. Because these are counting numbers or whole numbers. All right, so if you put both of them equal to 0, the left-hand side you have a0 plus a0, m is 0, you have a0 plus a0 over 2. Right? And this gives you 2a0. And this is 2a0 divided by 2, which gives you a0. And subtracting, you get a0 equals 0. All right, so we've calculated a0. It's equal to 0. Now what I'm going to do is I'll make n equal to 0, then I'll have am plus am. Right. That's a nice thing to substitute. Let n be equal to 0. And in the left-hand side, you have am, a subscript m, plus a subscript m. The n is 0. And here you have a2m. N is 0, so you have a0 over 2. All right, so on this side, you've got 2am, 2a subscript m. A0, remember, is 0. So this is a subscript 2m divided by 2. And you have a nice equation, a subscript 2m. A subscript 2m is 4am, 4a subscript m. All right, now I'm just going to keep track now of what's going on. And there's no ends in this, you see, because we made n equal to 0, but you have a relationship between a2m and am. So let's have a look at what you've got here. I'm going to keep that master equation. This part here was used to calculate a0, which we have done. Right? And now I want to use this one to make some calculations. So what do I have? If I put a0, a1, it's given that a1 equals 1, a2 A3, A4, A5, and so on. We know that A0 is 0, A1 is 1. It's given here. Now, A2, you can make M equals 1. So, it gives you A2 equals 4A1. If you make M equal to 1, then A2 is 4A1. A1 is 1, so 4 times A1 is 4. Right? And likewise, you can work out A4, put M equals 2. So you get A4, and M equals 2, so it's 4A2. And we just saw that A2 was 4. Sorry, I don't, oh, 4A1. Anyway, and A1 is 4. So A2 is 4. So you get 4 times 4 is 16. So this is 16. Kind of a pattern emerges here because you got A0 is 1, A1 is 1, A2 is 2 squared, A4 is 4 squared. Let's try to calculate A3 and see whether it is 3 squared. Okay, let's. Now, how do I get A3? I have to make these subscripts. I can make M equals 2 and N equals 1. Right. That will give me A4 and A1, both of which I know. So let's make M equal to 2 and N equals 1. Then I've got my A3, you see. So A3 plus, now M is 2 and N is 1, so this is A1. Equal to, here you have M is equal to 2, is A4 plus A2 all over 2. Now we have 1, 2, 4, we have, right? So this is A3 plus 1. A4 plus A2 is 20. 16 plus 4. A2 plus A4, you can see I've recorded it here. That's 20 divided by 2, that's 10. So A3 is 9. And there it is. It looks very strongly like AN is N squared. So our suspicion, in a competition, you would have said that we have the pattern, and with no further ado, you could have just written down that A2025 equals 2025 squared. And chances are you'll be quite right. But in our case, we don't want to go that route. We want to prove that AN is N squared. We have to prove it. Okay, now you see, I know that A2M, oh gosh, is now, oh yes, so this becomes a m plus n plus a m minus n equals, remember we said that this is 4 am and this is 4 an. I rubbed it out, but that's what we had earlier on. So it's 2 into am plus an. All right. Now, if I make n equal to 1, then we have these two numbers are quite close to each other. So you have am plus 1 plus a subscript m minus 1. And here you got 2 into a subscript m, and n equals 1. So a1 is 1. Now, you've got these numbers here, m minus 1, m and m plus 1 are consecutive numbers. So this can be a very useful formula here, right? Because each term, if I take am plus 1, it's equal to, you can write it in terms of the two previous ones. It's 2am plus 2 minus a m minus 1. So you got a given term is in terms of the previous, the one just before that, and this is the one just before that one. All right. Now, for instance, here, I can say that, so what's the rule? The rule is, let's rewrite this thing as 2a subscript m minus am minus 1 plus 2. All right, so I double the one just before it and subtract the one even before that one, then add 2 to it. So let's see. I double this, you get 32, minus 9 is 23, add 2, you get 25. And that's nice. See? So even and this is a very much faster way of working this thing out. If I try A6 now, I double this, which is 50, add it to this. No, 50. I subtract 16, 50 minus 16. 50 minus 16 is 34. Add 2, 36. There we have it. Right? So this thing here can be used to actually calculate the general formula. Right. And we're going to prove it by induction, mathematical induction, that required to prove in general an equals n squared. Right. We can guess that is the case, but we want to prove it for all possible values for n. And one of the ways of proving any formula is using the principle of mathematical induction. Okay, I've spoken about this principle in some previous talk. Let me say what it is. It's a very nice technique that you could use to verify a formula. In this case here, I suspect the formula, and to verify it, it's not a method of actually deriving formula. It's a method of verifying formula where you have a suspicion. And the way to do that is you verify for the 3 steps in the principle of mathematics. It's called the principle of mathematical induction. Right. Step 1 is test truth of the formula now. for the starting point, n equals 1. Now you can see A1 is known to be 1. It's given. And that is the same as 1 squared. So an equals n squared, n equals 1, n equals 1 works. So the step 1 is satisfied. Step 2 is assume. This is called the induction assumption. Assume that the formula is true for all numbers, say k, less than n. Make it n plus 1. Right? Actually, the induction says assume it's true for k, and then you try to prove that it's true for k plus 1. But what is really the other way of looking at it is prove is true for all the numbers from 1 all the way up to k, and then all the way up to n, because k less than n plus 1 means goes up to n. And then you say, if that is true, is the n plus 1, is it also true for the n plus 1 formula? Okay, and then prove. So if they use your assumption to verify the truth of the formula for k equals n plus 1. All right, so I'm going to calculate an plus 1. That's what I need to do. So a subscript n plus 1 according to what we have done here, this is twice an plus 2 minus a n minus 1, right? Because we know that for all m, this is true. If I replace m by n, this is what I got. But now I know that this formula an is n squared. For every k is smaller than n plus 1, you can use the formula. So this is 2n squared plus 2 minus, and you can use the formula for this as well. As long as your subscript is less than n plus 1, you can allow to use it. And now when you simplify this, you get n squared plus 2n plus 1. It's easy to simplify. And that is precisely n plus 1 all squared. So, in other words, that formula is true for n if you replace the n by n plus 1. Right? So verify the truth for n plus 1, we have done it, and therefore we can conclude that an equals n squared for all possible values for n, and in particular, this is a subscript 2025 is the square of 2025. And I see we didn't guess, we just suspected that the formula is that the nth term is n squared, but we only checked it out for n going up to 6. What about 7? What about 8? What about 189? Right? We don't know all that. So this method here, why this method works is the following. I just want to tell you why this induction method works, why you can conclude that now actually the step 4 is conclusion, The formula is true for all values of n. It has to be a formula for natural numbers, like this one. So let's see why this thing works. We have that A1 is 1, right? Now, we know, okay, A0 is not, that's not squared. A1 is 1 squared. So we know, assume the formula is true for all numbers less than n plus 1. So it's true for 0, it's true for 1, and therefore, according to this, use the assumption to verify that it's true for the next one. So we can use, because these are true, this step 3 says if it's true for all less than 2, as we can see, k equals 0, k equals 1, for all k less than 2, then it is true for k equals 2. That's what we proved here in step 3. Okay, now we know it's true for all these 3, therefore it's true for the next one. It's true for all these, therefore it's true for the next one. Now it's true for all these, therefore it's true for the next one. You see? So each time the truth of a whole lot of all the formula for all values less than a certain amount establish the truth for that particular amount. So that's way, this way you can go all the way for every possible n. And just using this little trick, it's a very useful trick to prove things. Okay, so let's just get on to question 5. Oh, so here I said we conjecture that an is equal to n squared. Okay, I have, all right, so this is my solution. I'm exposing it so that you can check to that. It's the same thing that I have done. Maybe even what I have done is a little bit better than what I've got here, because I didn't use all those funny looking formulae. I went straight to the main formula. All right, so question 5. Find the total number of different triangles whose angles are all integer numbers of degrees. Strange kind of a question. In fact, most of the time, when we work with triangles, we assume the angles are all integer, 30 degrees, 60 degrees, 45 degrees. We hardly say that the angle is 30.49376 degrees, usually integer degrees. But need not be so. The angle could be any angle, need not be an integer. So here the question is, you want all the angles to be whole numbers. How many such triangles are there? So it's a counting problem. Okay, so I'm going to let the angles be let's put it A there, B, C. So let angles be A, B, and C. All right, now the order doesn't matter. If you got a triangle with angles BAC or CAB, it's the same triangle. Right? The angles, the numbers are all integers. So we can assume we'll write these from the smallest to the largest. Okay, we can make this assumption because if all these are integers, then no matter how you mix them around, they'll still be integers. Okay, but we also know that a plus b plus c, because they are angles of a triangle, we know that they sum to 180 degrees. So we need to count now. How many such triangles are there? Well, see, if you have this, the value for a can't be more than 60, yeah? A greater than 60 is impossible. Otherwise, you have three numbers which are greater than 60 and they cannot be add up to 180 degrees. So we can easily say here that a is an integer that lies between 1 and 60. Right. Could be equal to 60. Right. If a is 60, then this will have to be 60 and this will have to be 60. Because it can't be anything bigger. The sum of the three is exactly 180 degrees. Okay. Now I'm going to fix a. Okay, now to understand the problem, I'm going to actually count for say example. Make a equal to say 40 degrees. Right. Now I want to count how many triangles there are with a 40 degrees less than b less than c, whose sum is 180. Okay, that's not very difficult to do because we can say if a is 40 degrees, then b plus c is 140 degrees. Now, a is less than b, so a is 40, so b will be greater than 40. Now, what can it go up to? The sum of these two is 140, but we remember b is less than or equal to c. So the largest value that b can have is 70, right? In which case b and c are both 70. B can't be 80 because otherwise c will be 60 and you want b to be less than or equal to c. Right? So the largest value is 70. So what does this mean? How many b's are there? Right? Number of b's is the number of integers. B has to be an integer from 40 to 70. Now you can count that. There is a nice way of counting this. All you do is subtract 1 from 40. The answer is not 70 minus 40, but 70 minus 39. That gives you 31. So for a equals 40, we know that there are 31 b's, and that forces the c's. For each b, you can get a c, right? Because then you got a and b, 40 and 31. Yeah. So there are 31 possible values for B. And for instance, the lowest value for B is 40. So you're going to have 40, 40, 100. And then the next value for B will be 40, 41. Now it becomes 99. Because the sum is 180, you see. So if you increase this by 1, you have to decrease this by 1. And so on. You got 40, 42, 48, 98, and so on. And it can only go up to 40, 70, 70. Right. And there are 31 of these. Now, but I'm not the A equals this B equals 40 is too specific. Let's just make that a general number now. We wouldn't give a specific value for A. Just remember when A equals 40, B equals the number is 31. A equals 40, number of triangles equals 31. Right. Now, remember I had 70. I had 180 minus 40 divided by 2. And there was 70 because A was even. So let me take A to be even. Any even number. Because I want to work with even numbers. Let A be equal to 2n. Now remember that, so then 1 less than equal to A less than 60 implies that 2 is less than or equal to A. Oh, I'm sorry. Your n can be at most 30. 2n is less than 60. So n is from 1 to 30. A runs from 1 to 60, but it's an even number. So it'll be 2, 4, 6, 8, all the way up to 60. So there are 30 values of n. All right. So if A equals n, I want to count the number of B's. How many B's? And I'm going to use the same technique. We saw what we did there. So what we do now is A equals 2n. I'm going to imitate this. A equals 2n. B plus C is 180 minus 2n. That's how we got 140. And therefore, remember we said the B can be only up to 70. So therefore, remember B is less than or equal to C. So the highest value for B is, remember we had 2B equals 140. That's how we get 70. So it's the same thing here. Now you'll have 2B equals 180 minus 2n, because it'll have to be, the last triangle will have to be ABB, right? Because B is always less than or equal to C. So B and C are the same. That's how you get 2B. And so the highest value for B is 90 minus n. There I had 70, and n is 20 in this case because we said A is, so therefore the highest value is 90 minus 20. So we are in the right track. And then we said, okay, how many B's are there? The lowest value for B was 40. So we needed to know how many numbers are there from 40 to 70. This time you will say the number of bees starting from b equals a, that's the lowest value, which is 2n. That's what we had 40, you see, 2n was 40. And then you go 2n plus 1, and so on, all the way up to 90 minus n. Now we need to know how many such bees are there, and we'll create some space. So what did we do? We said it's 70 minus 39, remember? So we took the last one. If you want to know how many integers are there in this set here, you take the last one. Ninety minus n minus, now here you have to take 2n minus 1. And we had 70 minus 39, and that gives you 91. 90 plus 1, 91, minus n minus 2n is minus 3n. Now we had, the number of bees was 31, because n was, in our case, a was 40, so n was 20. 20 times 3 is 60. 91 minus 60 is 31. So we're on the right track. So the number of bees is 90 minus 3n. Now that is when a is equal to n. So if a equals 2n, the number of triangles is equal to 91 minus 3n. Sorry, number of triangles is equal to 91 minus 3n. Right, so I want to know altogether how many triangles there are. Now the A is even, so let's just count the number for the even. Don't need these now, so I can take them out, hopefully. Okay, let's count the triangles, number of triangles altogether. A equals 2n, starting from, now remember, n was from 1 to 30. The A is 2n. Right, so for n equals 1, you have 91 minus 3 times 1. N equals 2, you have 91 minus 3 times 2. And that's the number of triangles. And all the way up to n equals 30, you have 91 minus 3 times 30. Okay? So what you mean by this is that when n equals 1, the lowest angle is, the lowest angle is 2n. So here, this thing here corresponds to a equals 2, and then we've got 88 such triangles. See, for A equals 2. For A equals 4, you got 91 minus 6, 85 such triangles. All right, so how many do you have altogether? So you have 30 numbers. You have to add up all these things. So add, you get 91 times 30 minus 3. Now here you can take out 3 as a common factor, going up to minus 3 into 1 plus 2 up to 30. And this is 2730 minus 3. Now the sum of all the numbers from 1 to 30 is 30 times 31 over 2, right? And we can calculate this one. It's 2730. 3 times 30 minus times 31, 2 goes into this 15 times. 15 times 31 is 465 times 3. So that becomes 1395. Subtract these two. So you have 5 plus 3. 3, 1. So this works out to 1,335 triangles. And remember, this is only for when n is even. Right? We looked at only those angles where A is equal to for A equal to 2, 4, 6, all the way up to 60. And we still have to count the other ones for A equals 1, 3, 5, all the way up to 59. Right? We still have to count how many such triangles there are in that case. In that case, I don't think I'm going to do this now. It's taken quite a lot of time. But just to give you an idea, here the general formula is A is not 2n, but it's 2n minus 1, because it's 2 minus 1, or 4 minus 1. So the A is this, so it becomes an odd number. And the values of A are still 1 less than or equal to A, less than or equal to 60. So that gives you 1 less than or equal to 2n minus 1, less than or equal to 60. And that gives you 1 less than or equal to n, less than. But now this is 61. 2n is less than or equal to 61. N is less than or equal to 30 and a half. But n is an integer, so you can do that. So you get the same values for n lying from 1 to 30. And again, you can do the counting and so on, which I won't do. And eventually, you can count how many there are for these. And once you do that, then you just add the two. So I'll just go to my solution. I'm sure I've done everything fully then. So there you see there you came to 1335. I stopped there. Now when I said A is odd, I came to this, and now you can use the same kind of an argument and count and so on, and sum all these numbers like the way I did. This time you got a 92, not 91. So you add these 30 numbers with 92 as your starting point, and eventually you get that there are more triangles with with having the odd A, not much more, 1365. And then if you want to know the total number of triangles, you add all the number of triangles which have got even A as well as the odd A, and those two are added. So the answer is actually 2,700. Okay. So that takes care of that.